Hi, I'm Alan, and today I'll be talking about clustering mixtures with almost optimal separation in polynomial time. This is joint work with Jerry Lee from Microsoft. Okay, so let me begin by setting up the problem with a few basic definitions. So a mixture model is defined as follows. So we have a class of distributions C, and then we consider a mixture of k elements from D, and it's given by a distribution of the following form. So we have mixing weights W1 through WK that sum to 1, and then k component distributions D1 through DK. And then the way we draw a sample from this mixture model is we sample an index according to the mixing weights W1 through WK, and then we draw a sample from the corresponding component distribution D sub I. Now, Gaussian mixture models, which we will focus on in this talk, are the special case when the family of distributions is simply a family of Gaussians with some mean and covariance. And actually, we'll consider an even more specific case where the covariances are all identity. So these are known as isotropic mixtures of Gaussians, or isotropic GMMs. So mixture models and mixtures of Gaussians in particular are very well studied theoretically and often used in practice as a way to model data from heterogeneous sources. A fundamental question that we can ask about mixture models is that of clustering. So more precisely, given some samples, say x1 through xn, from a mixture of Gaussians, what we want to do is we want to cluster the samples so we want to form groups of samples so that we group the samples together that came from the same component. So for instance, as a visual in the diagram shown, the different colors represent the different sets of samples from different components. And so, of course, in the clustering problem, we would not have these labels, and we would only see the data points when we want to recover these clusters. Okay. So of course, the problem of clustering is not tractable without some sort of separation conditions. So in particular, if we had two components that had a lot of overlap, then it would be information theoretically impossible to even hope to cluster. So in particular, we need to assume that the components of the mixture are separated in TV distance. So for isotropic GMMs, this turns out to be a particularly nice quantity to work with, since TV distance is equivalent to simply the separation between the means of the components. So more formally, we'll consider, say we have an unknown mixture of Gaussians, n is equal to sum of wi, n of mu I, and covariance is identity. So it's a mixture of k isotropic Gaussians, and it will define the separation parameter delta as the minimum separation between any two components. Now, the main question we'll seek to answer in this talk is we want to understand what is the minimum separation that you need in order to efficiently cluster. So before we talk about efficient algorithms, we'll first understand the information theoretic limit for clustering. This turns out to not be too complicated. So for simplicity, let's assume that all of the mixing weights are uniform. So the case for general mixing weights can be dealt with very similarly. And so when the mixing weights are uniform, it turns out that basically the right separation that we need to cluster is essentially root log k. This is both necessary and sufficient to obtain a clustering that's accurate to say 99% probability. That's 99% accurate with high probability. Okay, so now the picture becomes a lot more complicated when we instead look at computationally efficient algorithms. So first, note that in one-dimension clustering is very easy because the points have to be spread out in 1D. However, in high dimensions, the problem becomes a lot more complex. So if we don't care about efficiency, then we can brute force search in exponential and D time, where D is the dimensionality of the data. However, for efficient algorithms, actually people were very far from the information theoretic limit for quite a long time. So in particular, first in 1999, there was this result by Dasgupta that showed how to solve the clustering problem with separation of root D in polynomial time. This was improved in 2000 to a separation of D to the 1/4. And then, so it's slightly improved a little bit further to, instead of D to the 1/4, we can deal with the separation of K to the 1/4. So instead of the dimensionality, it only depends on the number of components. This was the state of the art for over a decade until a fairly recent line of works achieved the following guarantees. So if the separation is k to the epsilon for some positive constant epsilon, then these algorithms can provably cluster the data with runtime polynomial in D and k to the some polynomial in 1 over epsilon. So if the separation is k to the epsilon, then sort of 1 over epsilon goes in the exponent of the runtime. So this is like close to the information theoretic limit. However, it's actually like does not reach the information theoretic limit. And in particular, like if we wanted to reach the information theoretic limit, we would need epsilon to be something like 1 over log k. And these algorithms would require quasi-polynomial runtime instead of polynomial runtime. So the question that we'll seek to answer here is, can we cluster in polynomial time down to the information theoretic limit? Recall the information theoretic limit is root log k. Okay, so the main result in our paper is that essentially, yes, we can cluster in polynomial time almost down to the information theoretic limit. So more precisely, for any positive constant c, if the separation is log to the 1/2 plus c k, then there's an algorithm which takes a polynomial number of samples, runs in polynomial time, and recovers a perfect clustering of the samples with high probability. So again, this like essentially matches the root log k information theoretic limit. And so I stated this for I stated our theorem for a uniform mixture. Like, of course, our algorithm or our results all generalize to non-uniform mixtures, where basically everywhere where you have k, you instead have k over the minimum mixing weight. And then we also are able to generalize the result to handle shifts of any distribution. So shifts of a fixed distribution D satisfying the point rate inequality. But for this generalization, we require a mild additional assumption that sort of the mean separations are polynomially comparable, meaning that they're not like some means that are like fairly close together, and then some means whose separation is like exponentially larger than that. Okay, so now that I've stated our main result, I'll sort of move into the more technical part of the talk. So first, something that will be important to understand is sort of where previous approaches get stuck and why they can't reach the information, like why they can't cluster in polynomial time down to the information theoretic limit. So previous approaches are all based on something called the method of moments. So this is a pretty general approach. So at a high level, it works as follows. So at a high level, we first measure the moments of the mixture M. So i.e. like we draw samples and we measure things like expectation of x to the t. And then sort of the key fact underlying these previous algorithms is that, or the key intuition is that if the moments of the mixture are distorted compared to the moments of a standard Gaussian, then we can use this information about like where the moments are distorted or like how the moments are distorted to find directions that will then allow us to cluster. So to give some intuition for sort of where these previous methods get stuck at this like k to the epsilon versus like poly with like 1 over epsilon and exponent trade-off. So if the separation between the means is, let's say, k to the epsilon, then note that the component mixing weights are like 1 over k. So in order for like, say, one separated component that's like k to the epsilon far to actually like sort of show up and like significantly distort the moments, we actually need to go to moments of degree 1 over epsilon. So this is so that like the separation of k to the epsilon raised to the like 1 over epsilon power can sort of cancel out the like 1 over k in the mixing weight. So you actually do need to go out to moments of degree 1 over epsilon to detect these distortions when the mean separation is k to the epsilon. So this is sort of the intuition for where this like fundamental like k to the epsilon versus like needing to measure moments of degree 1 over epsilon, this trade-off comes from. So to make this slightly more formal, so these previous approaches rely on the following observation. So, okay, imagine that we have some polynomial number of samples from an isotropic mixture of Gaussians with separation k to the epsilon. Now consider a subset of n over k, so 1 over k fraction of the samples. And let mu s be the empirical mean of this subset of samples. So now the key fact is as follows. So if the empirical moments of this subset of samples, so that's the left-hand side, if the empirical moments of this set of samples matches the moments of a standard Gaussian for in all directions, then this subset of samples must essentially recover one of the true clusters. And again, the intuition for why this is true is like, so if you had like part of one cluster and part of another cluster, then sort of the separation of k to the epsilon would cause some distortion in the degree 1 over epsilon moments, and it would be impossible to match the moments of a standard Gaussian. So this is the core fact for previous approaches. And so the way these previous approaches like actually solve the clustering problem is they simply try to find a large subset of points whose degree up to 1 over epsilon moments match those of a standard Gaussian along every projection. So there are some, I guess, complex algorithmic tools for actually finding the subset of points. But at a high level, it suffices to think of it as just like, okay, we have this core fact about like finding a like nice subset of points, and like the algorithm will just like try to find such a subset of points. So now, what is sort of the barrier to this type of approach? So again, as I said previously, so when the separation is k to the epsilon, we really do need to look at degree 1 over epsilon moment information. So if we want to get down to say polylogarithmic separation, then we really need to look at moment information at degree t, where t is something like log k over log k. And so again, the key fact on the previous slide can be restated as follows. So it's really saying something about the moment tensor t sub t defined here. So the moment tensor is like simply the empirical average over all the samples in our subset of xi minus the mean and then tensor to the t. And so sort of the fact on the previous slide was really saying something about the inner product of t sub t with like v to the t for any unit vector v is upper bounded. So this is really saying something about like the injective norm of this like tensor t. However, there are like actually like tons of issues with like everything I've said so far when we want to like break this like quasi-polynomial time barrier. And so in particular, even writing down this tensor t takes quasi-polynomial time because it has quasi-polynomially many entries. And furthermore, there are even more difficulties that one runs into because when we're trying to estimate the entries of this tensor, we're like using degree t information, and a sort of naive or like any like natural or straightforward type of analysis will also require quasi-polynomial number of samples to estimate the entries of this tensor sufficiently accurately. So this is sort of like the key barrier that we need to break. Like previous algorithms really need to like access this degree logarithmic degree information, and they need like quasi-polynomial runtime to write down these tensors and quasi-polynomial sample complexity to estimate them. Okay, so now I'll move on and talk about our approach. So first I'll overview like at a very high level how our algorithm works, and I'll like delve into the sort of key idea about how we get around this quasi-polynomial time barrier. So beginning with the overview, so first we'll make a few simple reductions. So note that instead of working with the original mixture, we can simulate samples from the difference mixture, where we like simply take the difference between pairs of samples and then normalize divide by √2 so that this like difference mixture is still isotropic. So note that this difference mixture is still an isotropic mixture of Gaussians, and it has k choose 2 plus 1 components. So there's one component with mean 0 corresponding to when we drew two samples from the same component, and the rest have mean that are at least delta far from 0. So this is because we assume that the means of the original mixture of Gaussians are separated. So now to cluster the original mixture, it suffices to sort of draw samples from this difference mixture and then show how to detect if a sample comes from the 0 component or from some other component. Because then sort of to cluster the samples from our original mixture, you can simply test every pair to see whether they came from the same component or not. So for the rest of the talk, in a slight abusive notation, we'll instead use M to denote the difference mixture. And we'll instead think about this like detection problem for the difference mixture. So just to quickly reiterate, so we have the difference mixture where we have the zero component and then the non-zero components. So again, it's easy to check that we still have like inverse polynomially bounded mixing weights, and also that sort of all the non-zero components have mean like sufficiently far from zero. And now the problem that we want to solve is, given polynomially many samples from the difference mixture, want to detect whether the samples came from a zero component or a component that's far from zero. So at a very high level, our algorithm will work as follows. So given a sample, we'll just compute some function f. So this function f will be constructed later, but so we compute some function f, sort of what we want this function f to have we want this function f have the following properties, which are that f is small with high probability if x is from the zero component, and then f is large with high probability if x is from basically a non-zero component. And so f will be so we'll still use degree like log k information. So f will be a polynomial of degree like t is like log k over log k, but we'll construct f in a very careful way so that the noise doesn't swamp our signal. So we'll be able to get away with sort of just the polynomial number of samples and also polynomial runtime. Okay, cool. So now I won't be able to go into full detail about how we construct this like test function f, but I'll try to explain sort of the key idea in our construction and how we get around this like quasi polynomial time barrier for previous approaches. So the key like object that we'll need to estimate in order to construct our test function f is the span of mu I to the s. So again, mu I to the s is d to the s dimensional tensor, and we'll want to estimate the spans of these for s is equal to like 1, 2 up to like t equals like log k. So sort of our actual test function f will be based on our estimates of these spans. So it will involve like constructing some polynomial and then or constructing some tensor and then projecting onto this span. But really like the key object in our construction is really estimating these spans. So I'll focus on how we achieve this step for the rest of the talk. And so actually already when I wrote down this notion of like this span of mu I to the s, there's already the same issue that like sort of these tensors are quasi polynomially large when t is like log k. So instead of actually like writing down this span explicitly, we'll maintain these spans through projection maps that we'll maintain implicitly. So we'll have like projection maps pi sub s that project from d to the s dimensions to k dimensions, and we'll maintain these projection maps implicitly. So note that the span is k dimensional because there are only like k means. So again, for a slight abusive notation, for the rest of this talk, we'll work interchangeably with these s dimensional tensors and their flattenings as length d to the s, like length vectors. Okay, so the way we'll construct these spans and these projection maps, we'll do so iteratively. So first our implicit representation of the projection map, we cannot hope to like capture like full information, but what we'll maintain with our implicit projection map is that we'll maintain that it can be efficiently computed for like specific tensors. So we'll be able to project rank 1 tensors efficiently. So tensors of the form v is equal to v1 times ... times vs. So a direct product of vectors. So we'll maintain that our projection maps can be efficiently applied to these specific types of tensors. And so now we'll construct our projection maps iteratively. So assume that we've constructed like the first like s-1 projection maps. So we have a projection map onto the span of mu1 to the s-1 ... up to mu k to the s-1. And suppose that we can compute the projection map efficiently for rank 1, like sort of d minus or rank 1 s-1 dimensional tensors. So now our goal would be to construct a representation of like pi sub s so that we can efficiently evaluate it on rank one S-dimensional tensors. Okay, so first, so to sort of lift from S minus 1 dimensions to S dimensions, we'll just like do nothing in the last dimension. So this is simply what BS does. So we'll now project from D to the S dimension, so like an S dimensional tensor, down to D times K dimensions, where we apply pi sub S minus 1 on S minus 1 dimensions, and then do nothing on the last dimension. So that's what this matrix B sub S does. And now, we have, okay, so now we have a projection map from D to the S dimensions down to D times K dimensions. Now, in order to construct pi sub S, we want to project from D times K dimensions down to K dimensions. So we claim that it suffices to compute the projection of, or it suffices to compute the span of B sub S times mu I to the S. So the span of B's, which are like K vectors in dk dimensions. So to see why this is the case, why it suffices to compute the span of these B sub S times mu I to the S, can do some simple computations to verify that, indeed this span is exactly what we're looking for. So for the sake of time, I'll like not go through the computations too carefully, but they're actually like quite simple to verify. So now, anyway, so we had constructed this like map B sub S onto dk dimensions. Now we want to find the span of BS mu I to the S for like I equals 1 through K. So, okay, so the object that we'll actually want to think about is the following matrix. So we have M sub S is equal to sum from sum of WI and then BS mu to the S and then BS mu to the S transpose. So this is a D to the S by D to the S matrix. And so note that the span of this is a dk by dk matrix. And note that the span of BS mu I to the S are exactly the non-trivial eigenvectors, the span of the non-trivial eigenvectors of this matrix. Okay, so this matrix is not too useful when written as in its current form, but the key observation is that actually we can estimate something that's like very similar to the above. So we can estimate the tensor T sub 2s is equal to the sum of Wi mu I to the 2s. We can estimate this tensor just from samples, right? And then we can simply apply our projection map B sub S to this tensor T sub 2s, where we rearrange T sub 2s into a D to the S by D to the S matrix, and then we apply B sub S on each side to turn this back into a dk by dk matrix. And then once we rearrange once we apply BS on each side, we'll get exactly this matrix MS, and then we can simply compute the span of the non-trivial eigenvectors, and we're done. So now, again, so the projection map BS can be efficiently applied by the inductive hypothesis. The projection map BS can be efficiently applied to any sort of rank 1 tensors. So if we have a suitable low rank implicit representation of T sub 2s, then we can compute this matrix M sub S efficiently. So this is actually like highly non-trivial, but I'll just gloss over this now and say that like from samples, we can construct this low rank representation. Now, so we can put everything together, and our full construction is as follows. So again, it's inductive. So assume we have a representation of pi sub S minus 1, and then we have samples from the mixture M. So we, again, blow up this into like sort of an S-dimensional tensor, so do nothing on the last dimension. And then we estimate this matrix A. So this matrix A should be M from the previous slide. So we estimate this matrix, and then we simply compute this gamma sub S as a projection onto the top K eigenvectors of A. Now we simply output the composition of gamma and B, and as we show that this is exactly the projection onto the top K, this is exactly the projection onto the span of mu I to the S. So this completes the construction of sort of the key object in our algorithm. So again, maybe to better understand this construction, so we constructed everything iteratively, right? So unraveling one layer of the iteration, unraveling one layer of the iteration, we can write sort of pi of S is equal to gamma sub S, and then apply to identity times pi sub S minus 1. So we can keep unraveling this recursion further. So we actually have a sequence of S projection matrices that project from dk dimensions to k dimensions. So you have like gamma S minus 1, and so on, and sort of unraveling the whole projection matrix pi sub S, we can unravel it in the following form shown on the slide. Sort of it suffices to maintain separate projection matrices gamma 1 through gamma sub S. So this gives us like the efficient like implicit representation of this large projection matrix. Okay, so there are several additional complications that arise when we so there are several additional complications that arise when you actually try to do the full analysis. So due to time constraints, I'll not go over them too carefully here, but basically there are issues when there are issues when the means are very are drastically different. So there are large means and very small means, because then sort of once you add a little bit of noise, sort of the large means will wash out the signal from the smaller means. So you actually have to do an iterative procedure where you recursively cluster by clustering sort of very separated components first, and then cluster smaller separations later. And this is sort of why our techniques need an additional assumption when you try to generalize to arbitrary Poincare distributions, which is simply that we don't know how to do this recursive clustering step at the end, even though all of our other stuff does generalize. So there are a few natural open directions from this work. So one is naturally how do we actually obtain the fully general result for arbitrary Poincare distributions? And then also we can ask for mixtures of Gaussians with spherical but covariances at different scales. And then finally, perhaps a more open-ended direction is, so there are these techniques in this paper by Nicholas and Kane in 2020, where they solve not only clustering, but they solve parameter learning or a proper learning problem when even the components are not separated. So perhaps we can hope to combine our techniques with the techniques there and solve not just clustering, but also proper parameter learning for mixtures of Gaussians with sort of no separation assumptions. Okay, and so that's all I had for the talk, and thanks.